Right. Welcome everyone to the 51st meeting of New Directions in Group Theory and Triangulated Categories. Today we are very pleased to have Petter Bergh from NTNU Trondheim as our speaker. He will be talking to us about support varieties for finite tensor categories.
So thanks, and thanks for the opportunity to give a talk here in this seminar. So this is a talk on support varieties for so-called finite tensor categories. This is joint work with Julia Plavnik, who might be here. Yeah, she's here. And Sarah Witherspoon. So let's just start with the setup. K will be just a field, an arbitrary field, and C, or curly C, is a finite tensor category. So what does this mean? So a finite tensor category over K, I should say. So what does this mean? So first of all, it means that the category is a K-linear abelian category with finite dimensional Helm spaces. So it's K-linear abelian category with finite dimensional Helms. It's got finitely many isomorphism classes of simple objects. And every object has finite length, and every object admits a projective cover. Then there's this the tensor product, which is just the structure of a monoidal category. So there's a bifunctor. There's a bifunctor, which we should just call the tensor product, which is associative and bilinear. And there's a unit for this tensor product, which is usually written as a, say, bold 1. And that's a simple object. It's one of the simple objects. And we require that the endomorphism ring of this unit object is one-dimensional. We haven't required the field K to be algebraically closed, so we require instead that this endomorphism ring is one-dimensional, and this is what we need. And then finally, we require that C is rigid. So this means that every object has a left and a right dual. So let me just write that left and right duals, they exist. So if you take an object X, the left dual would be denoted by, say, X star like this, and the right dual by X star on the opposite side. And those are different in general. And so I won't go through the definition of duals, but the existence of duals, that's important. And then the abelian and monoidal structures are compatible. Well, I've already written that. Yeah, I've written that the tensor product is bilinear, so it's sort of there's a compatible structure. I mean, the abelian and the monoidal structure are compatible. So that's a finite tensor category and some properties. First of all, it's a Krull-Schmidt category. So every object decomposes uniquely into indecomposable objects. Let me just write it in this way, that the Jordan-Holder theorem holds. So you have unique composition series for every object. The category is quasi-Frobenius. So this means just that the projective objects are the same as the injective objects. The tensor product is bi-exact. So it preserves exact sequences in both arguments. And the projective objects, they form an ideal, so that if P is a projective object, then when you tensor with anything, it stays projective. So P tensor X and X tensor P projective for all objects X. And the last three properties here, those are consequences of the fact that C is rigid. A typical example, or maybe the most typical example, is when C is the module category of a group algebra. Finitely generated modules over the group algebra of a finite group. Where the tensor product is just the usual tensor product of a K, and the unit object is just the trivial module K, and then left and right duals, those are the same. Those are just the normal duals of modules. So we'll do support varieties in such finite tensor categories, and we define the support varieties in terms of the maximal ideal spectrum of the cohomology ring. So what's the cohomology ring? That's just the X algebra of the unit object. Let's denote it by H star. So that's the cohomology ring of the unit object. In other words, just the direct sum of all the X's. Where the ring or the product, that's the Yoneda product. Some facts. First of all, this is a graded commutative ring, just like for group algebras. So this cohomology ring is graded commutative. This was proved in general for a monoidal category by Suarez Alvarez back in 2004. So graded commutativity means that if you take two homogeneous elements, you can flip the order of the product, but you have to make up with a sign, depending on the degrees of the elements. So it's a nice ring, but even more so, it acts nicely on the cohomology of the category. So if you take any object, there's a ring homomorphism or a graded ring homomorphism from the cohomology ring into the X algebra of the object. Let's call this homomorphism phi sub X, where you just map eta to, say, eta tensor X. And the image here is contained in the graded center of the X algebra of X. So this means that when you map phi over and then you splice with something, an extension in the X algebra of X, that's the operation is graded commutative as above. So like this. And then it's been conjectured, and this is sort of the big conjecture in all of this. It's been conjectured by Ettinghoff and Ostrich back in 2004 that the cohomology ring is finitely generated, and all these X algebras are finitely generated over the cohomology ring. And because of this graded commutativity of the module action, it doesn't matter if you view the X algebra here as a left or as a right module over the cohomology ring. So this has been conjectured to hold, and if it does hold, then we say that C satisfies FG. FG for finitely generated cohomology. And of course, when C is the module category for a group algebra of a finite group, this is just the Evans-Venkov theorem from the 60s. (1961-ish). So we'll do support varieties now, where we use the maximal ideal spectrum of the cohomology ring, but let's modify the cohomology ring because, well, it's graded commutative. So since we have graded commutativity, if you take an element in a homogeneous element in odd degrees, then if the characteristic of the field is not 2, then it squares to 0. And let's sort of get rid of these elements that we don't need. So let's write H dot of C. This is just the even part when the characteristic of K is not 2. and the whole cohomological ring if the characteristic is 2. So this is a commutative ring in the ordinary sense. And if FG holds, so if this condition is true for the finite tensor category, it's also true when you replace the whole cohomological ring with this strictly commutative cohomological ring. And let's define M0 to be the unique maximal graded ideal of this new cohomological ring. I'll just refer to this new guy as the cohomological ring of C. So this is the unique graded maximal ideal. Because we have assumed that the degree 0 part is just K. And then we define support varieties as just the 0 set in the maximal ideal spectrum of certain ideals. So the support variety of an object X, we denote it like this. What's this? Well, let's keep M0 there always, and then take all the maximal ideals that contain the annihilator ideal of the X algebra of X. So that's the support variety. And let me just comment that we could have worked in projective space and then just skipped the M0 here. But when we don't, well, we want to keep M0 because otherwise objects that are projective, or the 0 object, for instance, would have an empty support variety, and non-zero projective objects wouldn't have the support variety of a non-zero projective object wouldn't necessarily be non-empty, and we don't want to distinguish those. So if we keep M0, then all the trivial support varieties, they just contain M0. When we don't impose any finiteness conditions, so when we don't assume that FG holds, well, then it's always true that the support variety of a direct sum is the union of the support varieties of the summands. So this always holds. And it's always the case that support varieties, they behave well with respect to exact sequences. So if we have a short exact sequence like this, then the support variety of any of these objects is contained in the union of the support varieties of the other two objects. It's also true that the support variety is stable under taking syzygies and cosyzygies. So the support variety of an object X is the same as the support variety of any syzygy of X, positive or negative. What happens if you take the support variety of a tensor product? Well, ideally, you would want this to be the intersection of the support varieties, but this is not at all obvious, and that's going to be part of the final, the final part of the talk. What you can see in general, or what you can say in general, is that this is actually just contained in the support variety of X. We don't even know whether it's contained in the support variety of Y. But if C is braided, then it's contained in the intersection. So why is this the case? Why is there seemingly a sort of a bias here? Well, if we go back, how did we define the support variety? It's defined in terms of the annihilator ideal of the X algebra of X. And the X algebra of X is a module over the cohomological ring via this map here. So what happens when you take a tensor product? What happens if you take a tensor product X tensor Y? Well, then you go from the cohomological ring via this map phi X tensor Y into the X algebra of X tensor Y. But how do you do this? Well, you map an eta to eta tensor X tensor Y, which by associativity is just eta tensor X tensor Y. So you can view this as first applying the tensor product of X and then tensoring with Y afterwards. So there's a choice involved here. And that's why the support variety of X, or the tensor product, has support variety contained in the support variety of X when we tensor on the right, like this. But when C is braided, it doesn't matter, and then the support variety of the tensor product is contained in the intersection. And also when C is braided, then the support variety of an object is the same as the variety of any of its dual. And I forgot to mention what braided means. Braided means that the tensor product is commutative, so you have sort of functorial isomorphisms from X tensor Y to Y tensor X. That's braided. It's not as strong as symmetric, so symmetric means that you have sort of functorial isomorphisms that's square to the identities. Okay, so this is in full generality, but in this generality, without the finiteness condition, these support varieties, they don't really, you can't you can't say anything about the objects by looking at the support varieties. But when C satisfies this FG condition, then these support varieties, they contain the homological information on the objects. So if C satisfies FG, then, well, first of all, the complexity of an object is the dimension of the support variety. So what's the dimension of the support variety? This is just the Krull dimension of this cohomological modulo this annihilator ideal that we used to define the support variety with. And what's the complexity of X? Well, it's a measure on the rate of growth of the minimal projective resolution of X. So it's the infimum of, well, it's the infimum of all non-negative integers C, say, for which there exists a real number such that the length of Pn, where Pn is the nth module in the minimal projective resolution of X, is bounded above by Pn C minus 1. So P dot is the minimal projective resolution of X. So in particular, complexity 0 means that you have a projective object, which is the same as having zero-dimensional support variety, meaning trivial support variety. So an object is projective if and only if the support variety is trivial. You also have realizability. So for all conical subvarieties, meaning that it's the zero set of some ideal, for all such subvarieties, there exists a module having that variety as a support variety. So all possible varieties occur as support varieties. So as a byproduct of this, for all integers between 0 and the Krull dimension of the cohomology ring, which is the complexity of the unit object, there exists an object having that C as complexity. That's just a consequence of 3 and 1. And let me just finally say that, okay, if the support variety of an object decomposes, then the object decomposes accordingly. So meaning that if the support variety can be written as the union of two subvarieties with trivial intersection, so V1 and V2. With trivial intersection, then X decomposes as a direct sum, where the variety of X1 is V1 and the same for X2. So this is what you can say when you assume that this that the category has finitely generated cohomology, and of course it's been conjectured then that all finite tensor categories have finitely generated cohomology. So the question that we've been concerned with lately is whether the tensor product property holds. So is it true that the support variety of a tensor product is the intersection of the support varieties? And we call this the tensor product property. And then the same example, it's true for the typical finite tensor category. That's a theorem by Avrunin and Scott. From 1982, 1928, that's a bit early. Yeah, so that's a theorem proved by Avrunin and Scott from 82. And we would like it to hold for all finite tensor categories satisfying FG. And what's the motivation for this? Well, if the tensor product property holds, then the support varieties or the maximal ideal spectrum together with the support varieties, they form a support data on the tensor triangulated category you get when you factor out the projective, so the stable category. So remember, every finite tensor category is quasi-Frobenius, so you can form the stable category. That's a triangulated category, and it's a tensor triangulated category in this sense. So you can talk about support data in the sense of Paul Balmer, at least when C is a symmetric tensor category. What do you want to do? We want to classify the thick or the thick tensor ideals of this stable category, this tensor triangulated category. If you want to classify the thick tensor ideals using this notion of support, well, then you basically want that the support variety, they form a classifying support data. So that is what we want. But in order for this to hold, what you will actually need is that the support varieties, they satisfy the tensor product property. So that's one reason why we're interested in this. And what we've been able to show recently is that if C is braided, and then satisfies Fg, then the following are equivalent. First, the tensor product property holds for support varieties. Well, this is equivalent to the tensor product property where you only assume that, or when you only deal with indecomposable periodic modules. And this is again equivalent to the following. Whenever you take two objects, X and Y, if the support variety or the intersection of the support varieties is not trivial, then the tensor product is not projective. This again is equivalent to the same statement, but where you only consider indecomposable periodic objects. So these are equivalent. So basically it means that when you want to, let's say, check whether a finite tensor category satisfies the tensor product property, you only have to deal with periodic objects, which are objects of complexity 1, at least when they're indecomposable. So why should this sort of reduction result be useful? Well, here's one corollary. If K is algebraically closed and the characteristic of K is 0, and C is a symmetric finite tensor category, so remember, symmetric means braided, so the tensor product is commutative, but in a very, very strong sense, then the tensor product property holds. And you can also show that Fg holds in this case, so you have this powerful theory of support varieties. So a proof of this is just an application of Deline's characterization of such finite tensor categories. He showed that for over an algebraically closed field of characteristic 0, the symmetric tensor categories are just equivalent to certain or representation categories of representations of Hopf algebras of a very specific form, namely as skew group algebras. So we use this then to show that the tensor product property holds in this case. And this was it, actually.
Thank you, Petter. Can we all unmute ourselves and thank the speaker? When you said this was it, you meant it was the end of the talk, right? Not the end of the corollary.
It was the end of the talk and of the corollary.
Okay. Do we have any questions for the speaker?
Petter, what happens if you have only one simple object? Do you know? Can you get any further with some of these questions?
Yeah, sort of, this would sort of correspond, I guess, to having looking at P groups, right?
Yes.
So yeah, this is very interesting, and we haven't thought about this, but probably or hopefully one should be able to say something more in this case. I agree.
I mean, one of the advantages that you get there is that is that the what was I going to say? Is that every thick subcategory is a tensor ideal.
Yeah.
Right. So that was the reasoning for my question.
And the answer is I just don't know. I mean, we haven't been thinking about this in particular, but it would be very interesting.
Right. Any other questions? What's the most difficult example of a finite tensor category, which is not for which we do not know if it has finitely generated cohomology?
You can take the category of finitely generated modules over any finite dimensional Hopf algebra. And you don't know if FG holds here in general.
I'm guessing there are some partial results.
There are a lot of partial results, but there's not one sort of big result. We would like sort of one big result here.
Mm-hmm.
Any more questions? Okay, in that case, let's thank Petter again for this wonderful talk. We have a talk next week by Teresa Conde, so I hope to see some of you there. Okay, bye-bye.